Okay. So that gives me the phi equal to pi over 3. Does that make sense? Right? So if this is pi over pi equal to 3, and this is pi over 4, guess what happened? Do you have a bigger cone or you have a smaller cone now? I mean, a wider cone or narrow cone? Is you have a wider, right? So the angle that this is 60, that's 45. So you have a bigger angles here. Okay? Yeah. All right. So basically, what I want to show you is it's this number here, right? It's this number will affect this shape of the cone at here, right? Yeah. Now, if you may have an equation like this. Let's say maybe z equal to phi minus. Right? Maybe you have a z equal to this. So can you imagine what kind of cone this time? What will be the difference between this cone and this cone now? So this cone, for this particular cone, it goes like this, right? It goes like this. So what will be this cone here? Inverted, right? So the needle side points up, right? Yeah. So this is basically the minus signs here. What that means here, right? Yeah. And the phi essentially is a shifting along the z-axis. Okay? Yeah. So the scale at here is essentially trying to what we're trying to let you know is you need to be able to visualize what the function, right? If the question gives you a function here, being able to sketch, okay, most of the simple ones here. Okay, so now let's take a look at an example here. Okay, so I need you to find the volume. Okay, volume of this region D. So this region D is x squared plus y squared equal to 4, and z equal to x squared plus y squared and xy plane. Okay. So the volume is sandwiched by the three things at here. Okay, three things here. Okay, so usually you will have this drawing, but I think let's draw this region here, right? Okay. First of all, xy plane, because that's just the bottom surface. So x squared plus y squared of 4, what does that give you? Circle, but in 3D space it gives you a cylinder, right? A cylinder. So it's a cylinder with a radius of 2. Okay? Yeah. And this z equal to x squared plus y squared. That's what we just had, right? It's a paraboloid. So you have paraboloid like this. So we're looking for here's a cylinder, right? This is a cylinder here. So we're looking at this region sandwiched by the three things. So apparently the region D that we're looking at essentially is the region D below this surface paraboloid, above the xy plane, and inside this cylinder, right? Inside this cylinder here. So you're basically looking at this one here, right? Yeah. Okay, so we're looking for the volume of this one here, and right, we'll talk about the next one here. Is that all right? So I have a drawing in here. Yeah. So this is another drawing, it's a better drawing than what I have here, right? This is basically inside that's what we're looking for, the volume, all right? Yeah. Yeah, this is a drawing from Wolfram Mathematica. I found that the plotting capability is much better in that software than Maple. Okay, so now let's look for the volume. If I want to look for the volume here, you lay down the layout. So now let's suppose I'm going to do this Z, RDR, and d theta, that direction, same as Euro, right? Yeah. Okay, so first step, if you do this, first step, draw the projection of the shadow of this solid in the XY plane. And I think this is pretty easy. So the shadow basically is a circle, right? It's a circle. So now the question is, what would be the radius of this circle? So that circle is what? That circle is the intersection between the cylinder and paraboloid, right? And the paraboloid. So actually, the cylinder is not going to change. The cylinder is always a circular shape all the way up. And it's going to intersect this paraboloid at z equal to 4, right? So this is a 4 at here. So basically, the circle at here is it's a same as this x squared plus y squared equal to 4, the shadow. Okay? Yeah. So this is basically the shadow here. Okay. So once you had a shadow, then within the shadow you draw a vertical line, okay, going up. Okay. So you draw this going up. Okay, until you meet the top one, and you keep going, right? Yeah. First contact between the line that you draw and the solid is give you the Z mean. Second contact gives you the Z max. So this first contact is where you started, and so the Z mean here is 0, and Z max is where you hit this top surface here, and that top surface is the paraboloid. And we're using polar. Yeah, by the way, why do you use the polar? Because here you do have a circular kind of a shape right here, right? Yeah. So the top one is this, and that function is the same as r squared. So the r max is r squared at here. Okay? Yeah. And then r and theta is pretty much the same procedure as before. So you draw reading lines out of this shadow. First contact 0, second contact 2. Sweep that reading line across the whole shadow. Find the theta angles, okay, bounds the shadow, so which is theta, which is 0 to 2 pi. Okay. So that's it. That's the layout, and then the integral itself should be pretty straightforward, and you should get 8 pi here. 8 pi. Okay. Yeah. Any questions? Yeah. So now you think it back about the typical procedure of cylindrical coordinates. So first of all, when you use cylindrical coordinates, and that's when you have a kind of circular kind of shape, either cylinder or a circle, right, got involved. Okay. And then it's the typical procedure of finding those limits, the integral limits, right? So 3 steps. Okay. Yeah. Come again? Oh, DZ, sorry. Yeah.
Could you just evaluate this one as like a double integral?
Yes, you can. Yes, yeah. So as we actually, that's a good point. I think we mentioned this at the beginning of this triple integral. Whenever you calculate the volume, right? Whenever you calculate volume, you can basically either use triple integral or use double integral, right? If you use double integral, then here's the region R. Here's the top surface f of x, y, right? So you're looking at this volume between this f, x, y and the bottom here, right? Yeah. However, if the question is specifically saying use triple integral to do this, then you use triple integral. Okay, so now we're going into the next coordinate system, spherical coordinates. So let's see what is a spherical coordinates first of all. Okay. So you give a point P in the 3D space. So we're going to define ourselves a set of spherical coordinates. It's rho, phi, theta. Okay. So you use the 3 different variables to describe this location of this point P. Now, what is the rho, phi, theta again? So you starting from the origin to where the P is, and that's your rho. Okay, so that's basically the distance from point P to origin. And what about the phi? Phi is the angle, okay, between z-axis and the line that you just draw here. And theta is when you drop this P into the xy plane and connect this one here, and this is your theta here. Okay? So that's the definition of these 3 variables. Now, be careful of the arrows here. Okay. So whenever we talk about an angle, there's always a direction of a positive direction here. So for theta, it's always a positive. It's basically when you start from the 0 or the x-axis here. And for the phi, and the z-axis is the origin. Basically, you're starting from there, okay, and going, which one? This is clockwise, right? Yeah, this is clockwise. So the phi here is clockwise. For the theta is counterclockwise. So this is not the only definition polar. In some textbook, the phi here is defined as the other side. Basically, not from here. Here is from here to there is the phi here, right? Yeah. Actually, maybe it's more makes sense when you define a phi from here to here. But our textbook define a phi as here, right? Okay. Because when you go from here, that's the counterclockwise, right? Usually, you treat the counterclockwise as a positive angle, okay? Yeah. So I'm going to still stick into the textbook definition reference here. So our phi is from the z at here up to where this the line, the rho at here, okay? Yeah. So we're going to use this thing here. So this is a polar, and the next question is, what is the relationship between the polar coordinates and the Cartesian coordinates? Okay? Yeah. Because ultimately we have to transform every information from Cartesian to the polar coordinates. It's actually quite simple. This is basically originally is x, y, z, right? And this point here is x and y, and this up distance here is z. So you look at this one here. How do we get this relationship here then? So basically, let's say if this is x here, okay, this is x, right? So that's x. So how do I get this x? So you can see the rho, first of all, x equal to this guy multiplied by cosine theta, right? Is this distance. If this is distance, r used to be r. So this r cosine theta give you the x. Okay? And the question is, where is r from? The r, you can obtain the r from this right triangle here. So this is a right triangle. Okay? And this is a hypotenuse, This is the rho at here. So this is phi, so that's phi here, right? That's phi. So the r at here is actually what? Rho sine phi. That make sense? See r equal to rho sine phi. Right? That's sine phi. See, this is right triangle here. Okay? And this is a right triangle here. And x equal to r cos theta. So now you can see now, so x equal to rho sine phi cosine theta. Okay? Is that clear? Yeah. This is important because you will have a formula of this, but I think you need to this is very easy. You don't understand the word geometry where you get the x. Even if you don't remember the formula, right? You can easily derive this one here. So that leaves us to the y. So what do you think of the y now? The y will be rho sine phi sine theta. Okay. So then how about the z here? It's going to be rho right triangle cosine phi. Okay. So this is the relationship between x, y, z and rho phi theta. Okay, according to our definitions. Okay, our definitions. Now, a couple of important things regarding this definition rho phi theta. Right? Yeah. First of all, okay, the rho not going to be a negative number. So rho is always greater than or equal to 0. Right? Because rho is the distance from origin to the point P. So the smallest is 0. Okay? Yeah. And second of all, okay, this phi angle. Okay, so this phi angle right here, okay, and we're restricting our phi, okay, to be within 0 and pi. Okay, 0 and pi here. So you'll see that why is it the case here, right? Yeah. And theta would be, the possible range will be 2 pi, right? 0 to 2 pi. Okay. You'll see the reason why we define this one here, right? So I'll reserve that. You might think is phi. Well, if you move this one to the other side, I could get a phi more than pi, right? Yes, you could. Okay, yeah. But in terms of this triple integral, you don't need that. You only need phi between 0 and pi. Okay, yeah. Is that okay? Any questions? Yeah, good. Okay, so now the next question is a couple of issues before we conduct triple integral. Number one thing is, just as before, I give you a surface, and that surface is described by Cartesian coordinates equation. And now the similar question is, if I give you a surface, can we derive the corresponding equation in spherical coordinates, right? Yeah. And the other thing is, where does the spherical coordinates is used, right, in most applications? I guess it's very straightforward. When you have a spherical surface, right, then you use these spherical coordinates. When you have a ball, you use a spherical coordinate. So let's say now I have a sphere, right? Let's say I got a sphere right here. So this sphere is x squared plus y squared plus z squared equal to 1. Okay. So what do you think the corresponding equation for this sphere in spherical coordinates? Rho equal to 1, exactly. Yeah, this is a sphere centered at origin with a radius of 1. So in spherical coordinates, it's basically rho equal to 1, right? Rho equal to 1. So you have a constant, that surface, you have a constant radius 1. Now, if you cannot suspect where this rho equal to 1 from, so what do? We're going to substitute the x here, substitute y here, substitute z over here. Okay? So it seems to be very complex. There's so many sine and cosine, sin and phi's here, right? But guess what? Actually, you have x squared, y squared. When you take a square, you have this trigonometry identity: cosine theta squared, sine theta squared equal to 1. So everything is cancelled basically, all right? So you end up with this rho equal to 1. Okay? Yeah. Okay. If I change this sphere slightly. Okay, so here's another sphere, right? So now, what's the difference between this sphere and this sphere? Where is this sphere located? Origin at 0, 0, 1, right? Okay, so this sphere, probably if you draw it, this is 1 and here, 0, 0, 0, 1 and here. So then you have a sphere with a radius 1. Right, that's a sphere here. All right? Yeah. Okay, so the next question is, what would be the spherical, what would be the equation in spherical coordinates for this one here, right? For this one. Okay? Yeah. So, how do we do that? What we can do is, we can do the same thing as I was talking about, just sub the x over here, sub the y over here, and sub the z over here. Okay? Yeah. So if you do that, okay, I think I'll let you to practice that. Okay, so sub x, y, z, okay, into here. Okay. So what you're going to end up with, you're going to end up with rho equal to 2 cosine phi. So one of the assignments, simple assignments, is to derive the spherical coordinates equation for a sphere. Okay. So for this one here, you end up with this. So rho equal to 2 cosine phi. Okay. 2 cosine phi. Okay? Yeah. I'm gonna just kind of slightly show you where this is from here. Rho equal to 2 cosine phi here, right? Yeah. So let's see, right? This is a sphere. I just draw it here. This is a sphere. And what is the top intersection point here? The z here is what? Equal to 2. Okay? Yeah. So then I'm gonna look at the relationship of rho and phi here, see if that makes sense or not. Okay? Remember what how the phi is defined? Phi is defined as the angle between z-axis and the line that you draw here, right? Okay. So now, if I coming back to this drawing here, okay, not very good drawing, but I'm gonna starting from here, okay? I'm gonna draw a line, okay, basically anywhere to that surface of the sphere. Let's see, I'm gonna draw it up to here, right? Okay. So to make it a little bit simpler here, so I'm going to draw it here. Maybe this is in the z-y plane. Okay, so I'm going to draw it here. So if I draw it here, so when I'm looking into the z-y plane, it's a circle. Okay, it's a circle here, right? This is z, this is y, and this is 2 here. So when I draw the line, I draw the line like this. Huh? Yeah. Is that good? Yeah, I draw the arbitrary line here. Okay, arbitrary, which basically means here I don't specify the phi angle, but I just draw this one here. That's the phi. Was that okay? Yeah. So then, according to the definition of the spherical coordinates, this is a phi. From here to here is what? What's this? From here to here. So basically you draw an arbitrary line out of the origin. Rho, exactly, that's your rho here, right? The distance from that point, to the origin, that's your rho. That's the definition of the spherical coordinates here. Okay? Yeah. So here's phi, here's rho, here's a circle. If I finish this triangle here, according to the geometry, this is a right triangle, right? This is a right triangle here. If this is a right triangle, and what's the distance from this side here is what? 2, right? So then, what's the relationship between these two? Rho phi. Right? See that? Yeah. So this is basically where that rho equal to 2 cosine phi from. Okay? So back to this question here, if you see it in the spherical coordinates, which says rho equal to 2 cosine phi, so what jumped into your mind here is actually it's a circle, right? Like this, centered at 0, 0, 1. All right? Yeah. Okay. So that's all one thing here. Now, how about that cone that we were talking about? This cone here. Z equal to root x squared plus y squared. So this cone in cylindrical coordinates, it's z equal to r, right? It's z equal to r. Now, if we wanted to have this spherical coordinates equation for this cone here, We actually derived this one here, right? What would that be? So go back to this cone right here. So wherever you draw this line here, there is an angle associated with these reading lines. But because it's a cone, so that phi angle is actually what? Doesn't matter where you draw, the phi angle is always a constant, right? It's always a constant. So you have the cone here. The cone is generated by sweeping a right triangle. Okay? So this line, the angle between this line and the vertical axis, is always a constant. So what angle value is that going to be? Depends on the coefficients that are here. Right? So in this particular case, the phi is pi over 4. In this particular, pi over 3. So back to this question here, when you have this, that spherical coordinates equation describing this cone is just phi equal to pi over 4. Right? Yeah. So you have a constant angle, okay, and anywhere, and that's basically describing a cone. Okay, is that clear? Yeah. Okay. So now we solve this problem now, sort of establish a connection between Cartesian coordinates and spherical coordinates. So the next question is, we're going to do this triple integral, right? Triple integral here. So your original triple integral is in x, y, z. Okay, in x, y, z. Or this is dx, dy, and dz. But what we need to do is, we need to convert everything, okay, into spherical coordinates, okay, into spherical coordinates. So I should probably write it in a separate line here. It's a little bit longer expression. Okay. So if I write it, okay, so what I'm going to do is, I'm going to replace the x with r sine phi cosine theta, r sine phi sine theta, and now r is a rho, right? So r here. And rho cosine phi. Okay, so we're going to replace this x, y, z in the function f with corresponding expression. And this dx, dy, dz, instead of dx, dy, dz, what you're going to have is d rho, d phi, d theta. So the only question here is, right, what shall we add it here to keep this dv over here same as this dv over here, right? Yeah. So when we talking about cylindrical coordinates, I use two different approaches. One is to use an infinitesimal volume to derive this dv here, right? Yeah. And the other approach is what? Using that. When I see the name, everybody's just like, Jacobian, right? So the other approach is we use the Jacobian to derive the transformation, right? Yeah. So same thing here. Actually, you can also do this same thing. You can derive this dv either using an infinitesimal volume or using this Jacobian, determinant of the Jacobian matrix. So I'm going to show you what the infinitesimal here just quickly. We're not going to go into details here, okay? Yeah. So this is what I mean by infinitesimal volume here. So you took a very small volume, okay, out of a spherical sort of a solid here, okay? The way to cut out this volume is slightly different from the way you generate the volume using Cartesian coordinates. So basically use the layers of the surface and the layers of reading lines to cut that dv out. And once you cut it out and to treat this small volume as a box, okay, as a square box or rectangular box, doesn't matter, then you basically multiply each side to generate the volume. And once you generate, you get this rho square sine phi d rho d phi d theta. Okay? Yeah, so that's the this approach here. So this is going to be just rho square, okay, sine phi at here. Okay, rho square sine phi. A better approach, well, actually, it's mathematically more neat, is to use this Jacobian transformation. Okay. So you generate your Jacobian J, okay, which is this dx. This is the determinant of Jacobian here. So dx over d rho, dx over d phi, dx over d theta, dy over d rho, dy over d phi, dy over d theta, dz over d rho, and dz over d phi, and dz over d theta. Okay, yeah. Then calculate the Jacobian of this one, this matrix, 3 by 3 matrix. So that gives you the same thing, rho square sine phi. Okay, so either way, the formula that you're going to get is calculating trivial integral in spherical coordinates require you having this term rho square sine phi here beside this is d rho d phi d theta. Okay. Yeah. Any questions? Okay. So okay, now once we get down to this approach, so then let's talk about doing triple integral, evaluating triple integral in spherical coordinates. Okay, so we're gonna talk about that through an example at here. So here's an example. So did you finish writing it here? Okay, so here's an example here. Here is this, it's an ice cream cone again, but there's a topping there, right? Okay, so what's this shape at here? It's this. It's yeah. So this shape is cut by. So basically, it's intersection. Okay, intersection of a cone and a sphere. Okay, it's an intersection of cone and a sphere. So the bottom here, it's the cone there. Okay, so the cone here is phi equal to pi over 3, and the top is the sphere there. The sphere is rho equal to 1. Okay, so now I'm kind of making use of what we just learned there. So I'm just representing the cone using one equation, which is in spherical coordinates, phi equal to pi over 3. I'm representing the sphere using just one equation, rho equal to 1. So if you finish the sphere, that sphere centers around the origin like this, right? Yeah. Okay. Yeah. So what do we need? We need to calculate the volume. Let's calculate the volume in here. Okay, of this ice cream cone. Okay, so when you already when you do this calculation here, just as usual, what you need to do is you need to lay down the order. Okay, so basically you have 3 variables: rho, phi, theta, right? Now the order in here, generally we start with the rho at here. Okay, not necessarily always, but it's more convenient to start with the rho at here. It could be theta and phi here, but we're going to use the order as d rho, d phi, d theta. All right. So here's the order. So we're going to choose this d rho, d phi, and d theta as order here. Okay, as integration order. If I choose this order here, so this is the steps you do. Okay, first step. Okay, draw the sketch of this solid in the xy plane. Okay, so that the shadow, okay, in xy plane. Okay, draw the shadow in xy plane. Okay, so once we draw the shadow now, okay, and we're gonna start these integrations. Okay, yeah. Step 2. Okay, so we need to find the row limits. Okay, row limits first. So how do we find the row limits? So maybe I'll draw the shadow first. So the shadow is this, right? So there's a circle in here, basically, in the shadow. Okay, so the drawing is not that great, but okay. So here's what I'm going to do. To find the row limits, here's the origin. Okay, here's origin here. Starting from origin, you draw a reading line across the whole region. So right out here. Okay, across this whole region. So basically, this line is inside that region. Okay, it's in it. Okay, it's in it. Okay, so what do we have here? So we draw this. Let's call this L1 maybe. Okay, we draw L1 across this region D. The first contact between this reading line L1 give you the row mean. The second contact between this L1 and the region D give you this row max. So in this particular case, row mean is row max. How much distance here is 1. Right? Because the top surface is a sphere, so it doesn't matter where you hit it. That's a constant radius, which is 1. Okay, so row mean 0, row max is 1. Okay, yeah. Second step. Okay. Second step is like before. You do a sweeping now. So you sweep this one here, okay? Sweep this. Sweep the line that you draw, but you start to do the sweeping from the z-axis. Okay. Remember how the phi angle is defined. The phi angle defined as the angle starting from where? It's the angle starting from z-axis, right? So you start from here. You do the sweep. Okay. You do the sweep. Find the mean angle and max angle for the phi that contains this solid. Okay? So you're starting from here, you sweep up over here, right? So where do you start? When you start here, it's already intersecting this region here, right? And then you end up at here basically. Remember, you don't sweep over here, okay? You don't sweep here. You start from absolutely from the z-axis, okay? Absolutely from the z-axis, up to where the edge is, okay? Up to where the edge is. So in this particular case, I started from here. I'm already there. I'm intersecting the solid, so the phi is 0, mean. Up to here, that's the phi max, right? That's phi max, okay? So what is the phi max then? So this is z-axis. Come again? 45 degree? No. All right, this is a cone here. So this is your phi here. So that's pi over 3. So that means, okay, so sweep the L1, okay, from z-axis, from z-axis, to find phi mean and phi max. Okay, keywords is you always start from z-axis. So your phi angle, your phi angle cannot be less than 0 degree. Okay, and phi angle cannot be more than what? Pi, right? Yeah. Okay, so now I got my phi mean 0 degree. and phi max pi over 3. Okay. So I'll explain this in a better way after we find this mean set here. Okay. Yeah. So the last step, this is basically the steps here. The last step is to find the theta limits, right? The theta limits. So theta limits is based on the shadow here. Okay, based on the shadow. So basically, you look at you draw a reading line out of the shadow. You strip the reading line, okay, and look for the range of theta that bounds the shadow. So in this particular case, my shadow is 360-degree shadow. So my theta will be from 0 to 2 pi. Okay. Okay. Yeah.
Would it be the same if your phi min was negative pi over 3 and your phi max was pi over 3 and you choose theta min as 0 to pi?
Okay, so okay, so what you're thinking is you're defining a basically a new set of a definition now. You know what I'm saying? See, when I'm going to explain it why I'm restricting the phi from 0 to pi. Okay, yeah, because when you're saying okay, is it equivalent to set? You're saying to set what the theta from 0 to pi, right? And a phi from where to where? Negative pi over 3 to pi over 3, right? Yeah. But when you see that, you're setting yourself a new standard, essentially. Okay? There's actually nothing wrong there. So why is the reason here is this? What's the spirit? What's basically the whole thing about doing integral? Doing integral is you're integrating over this region D, right? So basically, what do you want to do? You want to sweep through the region D, or you want to basically generate the region D, but without overlooking any corners of it. So how did I generate this region D here? See, this is how I generated it, right? Look at this one here. Remember the first step, what did we do? We drawed a line here, right? We draw the line. So basically, what did I generate? I generated a line here, right? And second step, what did I do? I sweep this line from here to here. So guess what we generated this after second step? We generated this one here, right? And last step, what do? We sweep this theta from 0 to 2 pi. So basically you rotate this one 360 degrees. Did you generate the region D at here? Right? And did we generate the region D with the redundancy? Redundancy basically, did you over sweep or did you over generate? No, right? So the integral is you don't over integrate. You only integrate where it's indicated, and you're not overlooking the corner here. That make sense? So you see, now if I define myself with different things here, if I say, okay, I'm gonna, maybe I say, if you insist, can we let the phi go from 0, instead of 0 to pi, let's say I'm going to insist the phi actually go from 0 to 2 pi. If you do that, let's say now I'm going to give you this case here. I have a sphere here. Okay, I have a sphere. How do you generate the sphere? Right? How do you generate the sphere? Let's say using SolidWorks. So what do? You draw a line here, right? You generate a line. Now if you say I'm gonna basically the second step, instead of letting phi, this is phi here, right? Instead of letting phi just go from 0 to pi, I'm gonna let the phi go from 0 to 2 pi. So what are we gonna generate? We're gonna generate what? A circle, right? We're gonna generate a circle. So after you generate the circle, then you sweep the circle by 360 degree. So what are you going to get now? You still get a sphere, right? Spherical object. But imagine what happens is you actually overswept. Can you imagine that? So if you try this, you can try this in your CAD software. If you try this in CAD software, you say, okay, in CAD software, I'm going to draw a circle first. Okay, draw a circle first. Then I'm going to do a sweep. By how much degree? By 360 degree, and it's not going to work. Yeah. 180 will work. Exactly. However, then we're not going to be on the same page as the definition of the spherical coordinates. So we have to stay on the same page here. The same page basically, that's the definition, right? And later, if you become an expert in mathematics, become famous, and you can call upon the whole world, here's my new definition. I'm going to let the theta, I'm going to let the phi to change from 0 to 2 pi, and let the theta from 0 to pi. So that would work too. Is that clear? Yeah? Yeah. So the whole idea is basically you don't oversweep, right? You don't oversweep. You don't oversweep this solid. You only want to generate a solid. Now, how do you generate a solid? Yeah, that's basically a different issue here, right? That's really a different issue. Yeah. Okay, so now my integral basically, okay, 3 integrals here: rho square, sine phi, d rho, d phi, d theta. Okay. So this whole portion here is dv, right? This whole portion dv. My rho goes from 0 to 1. My phi goes from 0 to pi over 3. My theta goes from 0 to 2 pi. Okay, to 2 pi. Okay. So this is a not very bad integral here. Okay. So let's see what do we have here. Okay. Okay, so here is this integral, the inner integral 1/3 rho cubed. Sub 0, 1 into it. So 0 to 2 pi 1/3 sine phi d phi d theta. Okay? Yeah. So that's very easy. I think you can calculate yourself. So pi over 3. Okay? Any questions? Okay. The key point is how you obtain the limits. To obtain the limits, basically you do the 3 steps. The 3 steps are to generate this solid region D, or to sweep through the region D. But at the same time, you have to stick to this standard that we have. We're all on the same page. The standard is the phi angle cannot be less than 0, cannot be more than pi. And rho has to be greater than 0. Okay? Yeah. So we have some applications this year here. I'm going to talk about the next lecture, but other than that, any questions?